Hello everyone, welcome to what will be our pre-lecture for lecture number 28 here. We're going to talk about what entropy is and also cover the laws of thermodynamics. So, if you remember from last video lecture, we defined entropy at the end of it, and entropy has this absolute value, which is important in that it gives us an absolute scale. Basically, we know what 0 is. And the entropy of our system will increase as our number of microstates increases. And so we're going to explore that a little bit more in this pre-lecture. Before we get there, I think it's important to go over the laws of thermodynamics. They are essentially a series of empirically derived, which is to say we've done experiments to determine them, observations, and they relate temperature, energy, entropy, heat, and work. And so we actually have laws 0 through 3, and so the 0th law states that if two bodies are in thermal equilibrium, then a third body would also be in thermal equilibrium with those two bodies. Simplest way to think of this is if we have two things at the same temperature, then by definition a third thing also has to be at the same temperature. It sounds a little redundant and obvious, but it is actually helpful in getting to some of the math behind thermodynamics. Okay? In the first law, that's our conservation of energy. So if we have a closed system, then the difference between the heat supplied and the work done by the system on the surroundings. So just a reminder, in a lot of thermochemistry and thermodynamics, we want to define our system and our surroundings. That's going to be equal to its internal energy. Basically, the 0th and first laws you don't really need to worry about for Gen Chem 2. We're primarily going to focus on the second and third laws. And so the second law states that all spontaneous changes cause an increase in the entropy of the universe. And the third law states that the entropy of a perfect crystal at absolute 0, which is, of course, 0 Kelvin, is 0. Okay? And so, like I said, we're going to focus on the second and third laws. And so let's dive a little bit more into them. And I'm actually going to start at the end. We're going to start with the third law here. And I just read you that definition. And so we can describe that mathematically as well. We could also describe that using kind of a model in our head. And so probably the easiest way to picture it is if we have a perfect crystal, something that looks like this without any defects. And if it is at 0 degrees Kelvin, which is more of a theoretical idea than an actually achievable place, what that means is our molecules would not have translation, rotation, or vibration energy at that point. And so once that is the case, if it were the case, if it were achievable, that would mean we would only have exactly one microstate, and that would mean the entropy of the system would be 0. And so again, this is how we define what absolute 0 is. It also gives us an absolute value for entropy. And so basically, if we can calculate the number of microstates, we can then figure out the entropy of the system. And that's one way to calculate entropy. This is a problem we're going to go through in class. So calculate the entropy of a 3-atom, 6-location universe in which all 3 atoms are different. Again, we'll go through that in class, but just something to start thinking about now. Okay? As we go from 3 to 2, the second law of thermodynamics deals with predicting whether or not a reaction will be spontaneous. And so, of course, we can predict that. And we know that all spontaneous changes cause an increase in the entropy of the universe. And so, again, if we express that mathematically, we would say something like the delta S. So just a reminder, when we have this triangle, that is the Greek letter delta. It is a change in the entropy of the universe. It's going to be equal to the change in entropy of our system, and that we add that to the change in entropy of our surroundings, and basically the second law states that this has to be above 0. Okay? And so what that means is for any process to occur, we must increase that entropy. And so that means we need to consider, again, our system and our surroundings. Think about if we had some water just kind of left out on the counter, we know that that's not going to spontaneously freeze. But if we put that into a freezer, it will spontaneously freeze. And so we need to define what is our system and what is our surroundings. And so in that case, our system in both situations is just liquid water. And then we have a freezer as our surroundings in one situation, and then just room temperature air in the other situation. And so in order to have a freezer or refrigerator, we are of course taking heat out of things, and we are using the coil system in a refrigerator to remove that heat and still increase the entropy of the universe. And that will cause a spontaneous freezing of ice because we are paying the entropic costs by moving that heat outside of the freezer instead of having it be inside. Okay? So another way we can calculate entropy is basically using values that we can find in a table. And so if you were to look in the back of your textbook, we have standard entropies that are measured for 1 mole of substance under our standard conditions that we talked about last unit. And we can calculate the standard change in entropy for a reaction by essentially taking the sum of the entropy of the products, subtracting the sum of the entropy of the reactants. I should also say that V here is actually the Greek letter nu. That just means our stoichiometric coefficients. So we need a balanced chemical reaction. When we do that, we should be able to get a delta S for any sort of reaction that we have an absolute entropy value measured for. Okay? Another thing with entropy that can be useful in predicting the entropy of a reaction or a phase change is different phases will have different amounts of entropy. So solids will have less entropy than liquids, which will have less entropy than gases, which all relates back to the number of microstates that they have. So in a solid, we have basically no translation, so we only have or rotation, we only have vibrational motion, so we have very little entropy in solids. Liquids are intermediate, and gases, of course, we have a lot of entropy relative to the other two. If you have two molecules in the same phase, the one with the greater molar mass is going to have more entropy. That is essentially because we have more protons, neutrons, and electrons. That is going to lead to a greater number of microstates. And if we have a chemical reaction, if, say, for example, our products, if we form more moles of products than moles of reactants than we started with, that would also increase the entropy. So that should say entropy, not energy of our system. Okay, that's it for the pre-lecture. Hope it was useful. Looking forward to being back with you. If you do have any questions, please let me know. Otherwise, I will see you soon.